All right, everybody. Let's talk about Chapter 3, Potentials. We'll start out with Chapter 3.1, which is introducing Laplace's equation. So we're about to get a little bit mathy, and we're introducing kind of the math that we're going to be doing in a little bit. So 3.1 is about Laplace's equation and trying to motivate what this equation does. So we're going to start by introducing the topic. We'll discuss Laplace's equation in one dimension, in two dimensions, in three dimensions, which are all the dimensions, I think, and then discuss the boundary conditions and the uniqueness theorems, which allows us to solve Laplace's equations. So the primary task, your job in electrostatics, is you start with a blob of charge, and you want to figure out what the electric field is due to those charges. Okay, easy. You put an electron, you set it on the ground, and you solve Coulomb's law. You use F is K Q1 over R, Q2 over R squared. You get the force between two charges, or if you have just one charge, you calculate the electric field due to it. Divide out your test charge, for example. And this is that electric field, the electric field of a charge distribution rho, whatever that charge happens to be as a function of r. Integrate that 1 over r squared, and you get your goodies. You get your electric field. Okay, but that's not so easy to do if you have unruly charge configurations. Okay, and that's not an easy integral to solve if you don't know your charge distribution easily. To make things easier, we figured out Gauss's law. We can exploit symmetry. We also can approximate the situation with simpler charges. But there's an actually an easier solution, possibly sometimes, which is to calculate the potential V. And we know from our triangle of relationships that if we have V, we can get E, we can get rho one way or the other. Okay, well, how do you get the potential? Okay, you integrate the same thing. It's an integral of the charge distributions, but it's 1 over r instead of 1 over r squared. So sometimes that is an easier integral to solve, but sometimes that's a tricky integral as well. Okay, so sometimes we're stuck. We might not know what the charge density is. If we don't know the charge density, well, we can't integrate it, can we? So we have to solve Poisson's equation, okay? And Poisson's equation is del squared V is equal to minus 1 over epsilon I times rho. But of course, I just said that, well, we might not know what rho is. But what if we aren't interested in a region where the charge is? We're interested in a region where there's a potential V, but there's no charge in the region where V is. So there's no source or sink connecting the electric field lines in the region you're interested in. Let's say between parallel plate capacitors, in that region, for example. There's a potential there, but no charge. So then we get Laplace's equation. And Laplace's equation is when there's no charge term on the other side of our nabla. So del squared V equals 0. That's Laplace's equation. Poisson's equation is here. Poisson's equation is del squared V is equal to 1 over epsilon naught times rho. But in a region where there isn't any charge, you still can solve Laplace's equation, del squared V, but now it equals 0 because there's no charge in there. So the important thing is this is where there's no charge in the region, okay? But it doesn't mean that there's no charge at all, because if rho is just 0, then V equals 0, rho equals 0, everybody's 0, there's nothing, okay? We're not talking about that. We're saying we have some charge, and we want to know what's the potential over here, for example. Okay, the charge is not in that region, but it's still generating a potential. And so we want to figure out what the potential is in that region, but we can do it without having to consider what the charge actually is. Okay, so if we can solve del squared V equals 0 in that region, it can tell us about the charge later, but we don't need to know anything about the charge in order to solve that equation. Okay, if there's no charge at all, obviously V is 0 and there's no point, but we're not talking about that. We're talking about where for the potential V in a region that is near charges. So there is a potential, it exists, but we don't know what the charge is. We just define a region that is surrounded, that doesn't surround any charge. Okay, and this should make a little bit more sense here in a couple seconds. The solutions to this equation, by the way, are called harmonic functions. That's just the solution to Laplace's equation. The general form del squared V equals 0, if you write it out, it's the partial derivatives of the potential with respect to x, y, and z in 3 dimensions. Okay, let's look at it in 1 dimension though. Let's say that our potential V only depends on one variable. So V is constant, but as you move in the x direction, it changes. Laplace's equation then, del squared V, we only have dv dx, d squared v dx squared on this thing equals 0. So that's what it reduces to, because it only depends on x. So dv dy squared is 0, dv dz squared is 0. So the general solution for this is the equation of a line. Okay, the general solution for this equation, d squared v dx squared equals 0, is v of x equals mx plus b. Okay, if you plug mx plus b in there, then the first derivative gives you m, the second derivative gives you 0. Okay, so that's a solution to the to Laplace's equation, and this just means the potential drops in a line. Okay, that's what it looks like. That's what a line is. Okay, hopefully we got that. So y equals mx plus b is a solution to this, or v equals mx plus b. But in order to actually get the solution, right, we need to know m and we need to know b. We have to we have to employ appropriate boundary conditions. So according to this graph, when x equals 1, v equals 4. That's a boundary condition. And when x equals 5, v equals 0. Those are our 2 boundary conditions. We know what v is at the ends, and then whoop, we just have to connect them in a way that solves Laplace's equation. That's a solution to it, and it turns out that the equation of a line is that. So you get your slope. You can specify those boundary conditions, which tells us the constant m is -1, and the intercept, the y-intercept, where when x is 0, what is y, is 5, and that gives us our solution. So v of x is minus x plus 5. This is a solution of Laplace's equation in 1 dimension. How wonderful. V of x is then the average, if you think about it. The potential at any point is the average of the potential above and below it. Okay, and that's what this graph is trying to tell you too. This point here, the point in between, okay, this point is the average of that and that. Okay, it's halfway between the two, x minus a and x plus a. Okay, it's the average value. What that means is that it continuously decreases from one point to the other point. It doesn't have any sort of loop, minima or maxima. That's a result of this, okay? So you can think of the potential at any point as just half of the value of the points above and below it, the values of the potential above and below it. Okay, this may seem a little bit weird, but all of this is telling you is that the potential always has to go down from a point. Okay, it can't go down and then up and then down. It has to keep going down. Okay, so Laplace's equation is an averaging instruction. It assigns to some point x the average values to the left and to the right of that point, or around it if it's a 2-dimensional surface or a 3-dimensional surface. The result of this, right, and this is the point, we're going to hammer this a couple times, there's no local minima or maxima as solutions to Laplace's equation. So whatever the equation is that you figure out for the form of V, you always got to go up from a point or always go down from a point. You can't go up and down and up and down. You don't get any sort of minima or maxima. The potential just keeps going down from your charges. And that makes sense. You can't have a charge and the potential starts going down and then suddenly the potential goes up. And no, it's got to continuously decrease from a charge. If you have two charges, the connection between them, the potential between them is smooth too. Okay, so you don't ever get you know, you just always fall down. You always fall down. If the potential changes as a function of two variables, so now we're in two dimensions, let's say as a function of x and y, now we have to use partial a partial differential equation. So we've graduated from the previous example, one dimension, which was an ordinary differential equation, just one variable. Now we have a partial differential equation because we have to solve something that depends on x and y. The solutions to this equation are infinite. You can have any sort of possible thing to this. So this isn't a great solution or a great equation to start with, okay? Think about a sheet. Any sort of sheet anywhere, as long as you have the edges bounded, okay, then that's a solution of Laplace's equation, okay, no matter what, since the edges are bound, that any surface like that satisfies Laplace's equation. So you can imagine any sort of surface. How do you know which one belongs to your potential? If any equation satisfies these two equations. Two dimensions, it's the same thing. The value at the xy coordinate is the average of those around the point. So what he does here in this is to draw this and says that the value at some point xy is, if you integrate around in a circle and divide by 2 pi r, you get the average value at that point, okay? And that's what that is. So if you draw a circle around the point xy, the average value of v on the circle is equal to the value at the center, okay? And that's what he's trying to draw here. He's saying, oh, you've got a surface. This is the boundary of it, okay? This surface is a solution to Laplace's equation, and then if we integrate and then divide by 2 pi r around that circle, the value at the center of it is the average value of that loop over 2 pi r, okay? So that's what he's saying there. It's the same idea that the value has to keep going down or up from some point. It can't you can't have local minima or maxima. And the way you can think about it is this: if I dropped a ping pong ball on this surface, it would roll down. Okay, it would roll off the edge here. It would not. It would just doop. It will. There's no spot where the ping pong ball can and just kind of sit. There's no spot for that. There's no pocket where the ping pong will sit. So that's what potentials look like around charges. If you're trying to visualize what an electric potential is, okay, it's something that has no local minima or maxima. So charges always flow away or towards. You can't have a spot where a charge just sits. And that's actually one of the homework problems that you have to solve, is that the Ehrenfast theorem, and I'll get to that. Earnshaw's theorem, sorry. Yeah, Earnshaw's theorem. And we'll talk about that in a second here. Okay, so in 3 dimensions, we have the same recipe. We're going to talk about it the same. The value at of the potential at some point r is the average value of a spherical surface around it. So how you do that is you integrate the value of the potential around a sphere on a surface of a sphere, and then divide by 4 pi r squared, the surface area of that sphere. That'll give you the average value on that surface, and then that value is the value at the point r, okay? Again, the consequence of that is that there's no local minima or maxima in the potential. Okay, so that's just something that is going on with these things. Okay, so he tries to do this little proof here, and it's interesting. What he says is, let's say you got a charge here, Q, and let's just integrate the potential on this surface. Okay, so what is V at any point on that surface? The potential is given by 1 over 4 pi epsilon naught Q over R. And what is R? R is this. It's the distance to the surface of the sphere, whatever that happens to be. Okay, in this case, this triangle, we're talking about centered at this point. There's our charge Q. We're centered at this point. What is the value of the potential on the surface of the sphere? Okay, so we got to figure out what R is. And the first thing we do is use the law of cosines to put R in terms of Z and big R, the radius of our imaginary sphere. So we're going to replace this R in terms of our constants, Z and big R, and then we can just integrate around theta and phi, keeping those things constant. Okay, so R squared is A squared plus B squared plus 2AB cosine theta, and we have A is Z squared and B is R squared. So we've got everything in there, so let's take our average value. So we have 1 divided by 4 pi R squared. That's the surface area of that imaginary sphere. Then we have Q, which is constant, over 4 pi epsilon naught, and then we have to just integrate over that surface, and we get Z squared plus R squared. That's what our value of R is, 1 over that, the square root of that, and then R squared sine theta d phi, and that's just looping, that's integrating over this sphere. If you do that, solve this integral and evaluate it from 0 to pi, then you get Z plus R minus Z minus R. Okay, goes away, and we're left with 2R, which cancels out the 2R down below. Z's go away, and you're left with 1 over 4 pi epsilon naught Q over Z. 1 over 4 pi epsilon naught Q over Z. That is just the potential Q over Z, where R is Z, and that's the value of the potential. If the average value, if we added up the potential on that surface divided by the surface area, we get the value at the center of this thing to be the average value on the surface of that sphere. Okay, so this is just trying to prove to you how the potential works. Okay, so it's a little bit weird. So that's true of anything. Okay, and this is an important thing. So problem 3.2 is one of the problems you have to do. So in one sentence, justify Earnshaw's theorem, which says that a charged particle cannot be held in a stable equilibrium by electrostatic forces alone. Okay, so the way to think about this, the reason you can't do this is because there's no local minima or maxima. That means there's no pocket for the potential to set a charge in. Okay, the charge is always going to find a way to roll down the hill. Okay, so the question is, where is the leak then? How does the charge, if you plopped it at the center of this cube of what direction is this thing going to fly out? How is it gonna, where is it gonna roll down? Okay, so this is the limitation of Laplace's equation in 3 dimensions. It's difficult to imagine what rolling downhill in 3 dimensions looks like. Okay, what does the 3-dimensional vector field potential thing look like? So anyway, think about that one and try to figure that out. All right, so then we get to the sort of the nuts and bolts. So I've been telling you so far that Laplace's equation has infinite solutions and anything goes. How do we figure this thing out, right? So thankfully, there's a couple of uniqueness theorems, which means that we can find unique solutions to Laplace's equation for our potential if we specify the boundary conditions. And that just means specify the value of the potential on the boundary. Okay? So we cannot determine the potential by Laplace's equation alone. We need to specify appropriate boundary conditions. So the question is, what are the boundary conditions? In the 1D case, it's easy. We just have to determine the slope and the intercept. You have got two arbitrary constants. They're pretty easy to figure out. But in 2 and 3 dimensions, we have these partial differential equations, and we have to figure out a bunch of things so that all our constants work out. So the good news is we got a theorem, as we typically do, and it's called the first uniqueness theorem, and it helps us define a solution to Laplace's equation. It says that we can uniquely determine the solution to Laplace's equation in some volume V if we can specify the value of V on the boundary surface. So in other words, if we know, for example, the potential here is plus 5 volts and the potential here is 0 volts, then we can figure out what the potential looks like in between these things. We know the edge at this point, we got to have 5 volts, and at this point we got to have 0 volts, and those things could be spread out in X and Y. So we can figure out what the potential is on the inside, and that's easy, right? That's an easy one. We already know what that is. But when we get to a little bit more difficult geometries, let's say we've got a charged thing here, a charged thing here, and a charged thing there. Woo! How do we solve that? That's not something we learned in Physics 101. That's a fancy capacitor thing. Okay, how do we figure that out? Okay, so that's it. We're gonna talk about that. You got, let's say, plus 5 volts here, 0 volts here, and minus 5 volts there. What's the potential look like on the inside? Okay, and that's what we're gonna be solving. And Laplace's equation and the uniqueness theorem allows us to do that as long as we again specify the potential on the boundaries. Okay, so in other words, if we know what the potential is on the surface, we can determine the value of the potential at any point within the volume. So he does this example here. Show that the potential is constant inside an enclosure completely surrounded by conducting material, provided there is no charge within the enclosure. So he's saying we've got a conductor, let's say a sphere. We want to show that the potential is constant inside this thing. It's a conducting material, provided there's no charge within the conductor. So we know by definition that the potential here is constant. Let's call it V0. And we know that the electric field on the inside is 0 because we've done that. We always know that. We can think about anything here. The potential inside, in order to satisfy this, is V inside equals the potential on the outside. Okay, V equals V0, and that's the solution. Okay, he says it doesn't take a genius to think of one solution to this problem. V equals V0 everywhere. The uniqueness theorem, though, guarantees that that is the only solution. So we did this problem where we had a conductor and we said, what's the electric field inside? It's 0 inside a conductor. And then we know that the potential inside is constant. Okay? That, again, it satisfies our equations del squared V equals 0 or del squared V equals minus rho over epsilon naught. These two equations lead to those solutions. Okay, so and then he says same result we found in section 2.5.2. So you can go back and review that real quick to see the relationship between these two things. Okay, so in the next section 3.2 we talk about the method of images, and that's when we learn about the power of this theorem, because if a solution satisfies Laplace's equation and has the correct value of the potential on the surface, it does not matter how you come by it, that is the right solution. So in the method of images, we do some crazy tricks and almost magic things, and you think, how can that be? Some tricks to solve the problem, but it's the correct solution even though we come by it making an unrealistic setup, or a setup that it doesn't seem to initially correspond to the problem, but it creates the right boundary conditions, and so we can get the solution to it. And so that's the main idea. Okay, so there's a corollary to the boundary conditions in uniqueness theorem, the first uniqueness theorem. if the potential in a volume is uniquely determined, or sorry, the potential in a volume is uniquely determined if we know the charge density in the region and the value of the potential at the boundaries. So in other words, he's saying that in the previous thing, we could figure out the potential del squared v equals 0 if we knew the value of the potential on the surface and the surface containing the volume. If there's no charge in there, we've got it. If there is a charge in there, as long as we know the charge, we can figure out what the form of v is between the charge rho, whatever that is, and our surface. So we can figure out what the potential is everywhere in between, as long as we know what the potential is at the surface. Well, you know, at infinity, the potential is 0, so that's a boundary condition. Okay, so these are some tricks we're going to learn when we can apply certain boundary conditions. All right, so 3.1.6 is the second uniqueness theorem. So the simplest way to set boundary conditions for an electrostatic problem is to specify a conductor. We connect it to ground. Boom, we've specified V on all our surfaces, and now let's solve the problem and get what V looks like in between the two surfaces. Okay, again, it's pretty mathematical, and we're going to solve that problem here soon in the next section. So the second uniqueness theorem says that in a volume V surrounded by conductors and containing a specified charge density rho, the electric field is uniquely determined if the total charge on each conductor is given, and the region as a whole could be bounded by another conductor or unbounded, go off into infinity. So what he's saying here is that we can figure out the electric field, we can determine what it is if we know the total charge on whatever these surfaces are. So we've got a volume here, and we're going to specify the outer boundary. Either it's there or it's off at infinity. But if we know what Q is, if we know the charge, the total charge, then we can specify what the electric field is. And again, that just has to do with Gauss's law, and we've kind of already done this, so this isn't a crazy thing, but it's a useful thing to know, is that as long as we specify the charges, Q, we can get the electric field in the region between them using this rule. So what he does here is he says, okay, well let's figure out the Gauss's law for this charge, Qi, Qa, Qc, Qb, right? These are all the relationships here. And he says, okay, well, let's look at the difference. So we calculated it for, let's say, the ith surface. We added everything up. We got the region where there's no charge, and in the region between the conductors. So you do that, blah, 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 blah. Then he does the product rule to simplify the integral, and you get that the integral simplifies to this. You integrate the magnitude E3 squared over all space, but we know that this has to equal 0, okay, and there you go. The only way that E3 can be equal to 0 is if E1 equals E2, and so basically what he's showing you is that this works, and this is, again, it's a little bit proofy, it's a little bit mathematical, so it's not super exciting, but the point is that this is a very powerful trick, that we can, if we can just specify the potential, 5 volts here, infinity, 0 at infinity, we can specify our boundary conditions, then we can calculate what V is in the region between it, okay? And so we're going to so this is all math and conceptual stuff, it seems like. We didn't really do anything. We didn't solve many problems. Method of images, 3.2, and then after 3.2, we get into separation of variables. So 3.2 and 3.3 are actually solving these problems. And there you go, there's an example. We've got a potential of 0 up here, a potential of 0 here, but then a potential v, which is a function of y on the zy plane. What does the potential look like in there? Okay, so then we're going to learn the tricks on how to actually get what the value of v looks like, and it's a little bit hairy, but it's kind of fun to actually get the solution, and it looks pretty neat. Okay, so we're going to get into all that. If this was a little bit dry and boring, it's just trying to motivate what we're about to do. Okay, so see you guys next time.